Okay, so we have previously seen some mechanical pressure sensors, and usually those sensors use large structures, either a solid or a liquid structure. The pressure is applying on them, and then they generate some deformations, so the deformation can be directly uh, measured or visualized. So that's the basic principle. But because they are usually using large structures, so their dynamic performance or their dynamic response is not very fast. So if you want to connect a pressure sensor to a computerized data acquisition system, so obviously you want to utilize some electrical pressure sensors. So in the following few slides, we will see a few type of electrical sensors. So their principle is quite similar to the ones you have seen, because basically you are applying pressures to a smaller structure. So that's why usually electrical pressure sensors has a faster dynamic response, and then the structure will be deformed or generate a mechanical signal, and then this mechanical signal can be finally measured or converted into an electrical signal. So that's the basic principle of electrical pressure sensor. So before we look at those details of the sensors, let's look at a basic structure for pressure measurement that we usually used. So this structure is so-called diaphragm. So it's basically elastic membrane. So the word is diaphragm. Sorry about this. So the word is diaphragm. It's basically an elastic membrane where we can apply two pressures on both sides, P1 and P2. So this is a schematic of diaphragm structure. So usually the shape is a circular shape, and once you apply a differential pressure P1 and P2, so the difference will actually deform this diaphragm to generate a deformation, and this deformation can be finally measured using some typical sensing mechanisms you have seen before. For instance, you can attach a thin film strain gauge on the surface of the membrane, so you can measure the deformation. So that's a strain gauge based pressure sensor. So before we look at the details of the sensor, let's look at the mechanics of the diaphragm. So in terms of the material of this diaphragm, you can choose different type of materials, but the material selection is usually depending on the desired measurement range, the pressure range, and also sometimes this diaphragm will actually in direct contact with some fluids. So it could be simply gas in here, but it could be also some fluids in the chamber. So if there's a direct contact with the fluids, you have to consider the characteristic of the fluids. For instance, if it is a corrosive fluid, you might want to use a specific metal to deal with that. So that's also depending on the fluid. And because usually this diaphragm is in a smaller size and is very thin, so it has a very high natural frequency. So that's why the dynamic response wise, so it has a faster dynamic response. So it's suitable for both static and dynamic measurement. Now let's look at the mechanics of the diaphragm. So this is actually the formula we can use to calculate the maximum deflection of the diaphragm if it is a circular shape. So the maximum deflection will happen here. So that's the Y maximum. And you have a pressure difference P1 and P2. So the difference is P1 minus P2. So we can actually calculate the relationship of this sensor input and this output. So this is a relationship we can use, but you need to know this formula has an underlying assumption, which is the small deformation assumption. So that's why if you need to make sure this maximum deflection here has to be small enough. So if it is too large, the diaphragm will be not in the small deformation range. So this equation will not hold anymore, or will be not very accurate anymore. So that's why this is the condition for those formula to hold to give you an accurate result. So your maximum deformation in the center of the diaphragm has to be smaller than 1/3 of the thickness. So T is the thickness of the membrane. Now let's go back to this formula. So I have a few parameters. As I told you, y is the maximum deformation in the center of the diaphragm, and the mu is the Poisson's ratio. R is the radius of the diaphragm, and P1 P2 is the pressure difference, and E is the Young's modulus, and T is the diaphragm thickness. So my requirement here for this mechanics of the diaphragm is basically you need to know how to use this formula. I don't require you guys to memorize it, but you need to know how to use it, and you need to know which parameter is which physical quantity, and also you need to understand this is the small deformation condition. In order for this equation to be accurate, you need to satisfy this condition. So the next slide. Okay, let me add the slides figure. Okay, so this is an example which can help you to understand the mechanical model of the diaphragm. So we are designing a diaphragm pressure transducer. So we know the maximum absolute pressure applied to the diaphragm is 1.4 megapascal. And usually this diaphragm pressure sensor has two inlets. So this maximum absolute pressure is applied to one inlet, and the other pressure inlet is open to atmosphere. So that means, so what we are measuring is actually the gauge pressure. So this atmosphere, this is the value of the atmosphere, or expressed in psi. And also we know the material property of the diaphragm. So Young's modulus is 200 gigapascal, and the Poisson ratio is 0.3, and also the diameter of the diaphragm is 2.5 centimeter. So the question is, please find a proper thickness of the diaphragm so that the maximum deflection is still within the range, which make this equation, make the diaphragm mechanical model to be accurate. So which is smaller is within 1/3 of the thickness. So we are basically selecting thickness to make the deflection small enough, or in other words, to make the thickness large enough. So that means if you go back and then you look at this condition here, so the maximum deflection has to be smaller than 1/3 of the thickness. So if we make it to be equal, and this will be the critical condition, right? So that's the critical condition. So that's why we make y maximum equal to 1/3 of t. So that's why this is y maximum equal to 1/3 of t, and this is the y maximum formula. So if we make this equation, and we can actually solve a value of t here, because t can be regarded as an unknown, and all other values we know it already, because we know P maximum, we also know the atmosphere pressure, we know the Poisson's ratio, and we know the radius, Young's modulus. So the only unknown is actually the t value here. So if we solve this equation, we can calculate the t value, which is 1.068 millimeter. So that solves the critical value. So this means this is a critical value, or is a boundary value of t. So now my question is, if this value should be the minimum or the smallest t value we should select, or this should be the maximum t value we should select, because we are basically required to select a proper thickness, right? So think in this way, because we want y maximum here to be small enough. That's, in other words, we want the t value to be large enough. So that's why this critical value is actually should be the smallest t value we should choose. So any t value we choose which is larger than this critical value here will make this condition hold. So that's why this value is actually the smallest thickness. Okay, so now let's look at a few types of diaphragm-based pressure sensors. So the first one is using strain gauge as the sensing mechanism. So if you look at this schematic, so you have one inlet here and one inlet on the right side. So in the middle you have a diaphragm. So for this diaphragm, if you apply a pressure source in the left-hand side and then use the right-hand side as a reference pressure, so this right side chamber is actually can be connected to any type of pressure source. For instance, you can simply expose this inlet to the atmosphere. So what you are measuring will be the gauge pressure. But if you seal it, let's say if you seal this and then you make the inside to be completely vacuum, so this pressure sensor will be an absolute pressure sensor. So once you have a pressure difference applied to the diaphragm here, so the diaphragm will be deformed, and then you can actually attach a strain gauge to the surface of the diaphragm, so the strain gauge can measure the deformation of the diaphragm. So this is another schematic showing you so the arrangement of strain gauges. So this is one, this is another one, and if you add another two on the bottom, you can actually form a full beam Wheatstone bridge circuit, which give you the maximum sensitivity. And those are the photo. This is a photo of different types of pressure sensors based on strain gauge. So you can see this guy only have a single inlet, so that means it is an absolute pressure because the chamber inside is sealed. Of course, it could be sealed under vacuum. That means the reference pressure will be zero. It could be also sealed at a constant pressure, so that will be a non-zero reference. And also you will find out another type which has two inlets. So it looks similar to this guy. It's basically you can connect one pressure source to the inside to one side and another one as the reference to the other side. So it can measure a differential pressure. And besides strain gauge pressure sensors, we also have other types of pressure sensors. For instance, you can have a capacitive sensor. So capacitive sensor, in the motion sensor part, you have seen that. So what is the principle of the capacitive sensor? So basically, you have a parallel plate here, and if one of the plate is fixed, the other one is suspended. So actually, if you apply a pressure if you make this structure to be the diaphragm, and this structure can actually be deformed up and down, right? So if you use a different color to indicate the deformation direction, so the top diaphragm can be deformed. So the gap size here will be changed. So that you can measure the capacitive change due to the pressure applied to the top plate, and then you can measure the pressure value. So and similarly, if you have a lateral displacement, you can also measure the pressure value. But usually this configuration, this vertical configuration is more popular in pressure sensor designs. So here is a schematic of one type of pressure sensor. So you have a diaphragm here, that's a diaphragm, and then you have a fixed plate. So those two form a capacitor. So once you apply a pressure here, and then you have a reference pressure, so this diaphragm will be deformed, and the gap here will be changed. So you have a gap here. So the gap here will be changed. So you can measure the capacitance value of this structure, and then you can correlate this capacitance value, the change of this capacitance value to the pressure. So that's one type. And we also have another type here. So this is your membrane. This is your diaphragm membrane. and then attached to the membrane, you have a pressure balloon below, which actually is connected to a pressure port. So when you apply a pressure into this chamber, and this chamber will move up because of the pressure. So this will finally this diaphragm will be deformed up. So if you look at the capacitors, so you have one pair of capacitor on the bottom side, you have another pair of power plate to form another capacitor. So once this diaphragm deform upward, let's say this is your deformed diaphragm, so the gap on the top will be decreased overall, and the gap on the bottom will increase. That means finally your top capacitor, if this is your delta 1, so it's the change of the capacitance value will be larger, will be positive because the capacitance here is increasing. And similarly, the capacitance here is decreasing because the gap is increasing. So the change of capacitance here is smaller. So if you sum up the change of the two capacitance values, you will have a large output. So this type of capacitive sensor, we call them differential capacitive sensor. Differential capacitive sensor. So differential sensor is basically you have one parallel plate and the other parallel plate. Once you have this deformation, one capacitance will increase and one capacitance will decrease, and then we sum up the two changes, and that give us a better output or give us a higher sensitivity. So just remember, differential capacitive sensors will have a higher sensitivity than a simple parallel plate capacitive sensor. Okay, so we have seen strain gauge pressure sensors and capacitive pressure sensors. We also have piezoelectric pressure sensor. So this is a cartoon you have seen before, and once you apply a force or any load to this piezoelectric material, it will generate a voltage. So if you can imagine, if you apply a pressure difference at those two surfaces, you can easily measure output voltage from the two surfaces here. So that's the principle of pressure sensor. You apply a pressure here, and then you measure output voltage. So this is actually the voltage generated, and then this is the pressure difference between the two surfaces, is the pressure difference. And then this is the thickness of the crystal, and G is the voltage sensitivity. So G is the voltage sensitivity. That's the equation usually we use to calculate, to design the piezoelectric pressure sensor. So this is a practical design, is a schematic of a piezoelectric pressure sensor. And the material here is the crystal, is the piezoelectric material. And this is actually a diaphragm. So if you have a pressure applied to the diaphragm, this material, this block will be compressed. So it will generate a voltage, and you can measure the voltage here. But I want to let you know, actually this looks like this diaphragm is hard to deform. So this, because this figure is from the textbook, but it doesn't really reflect the real design. So the real design should look like that. So this is basically the structure here, the diaphragm structure is not the real one, so it is simplified. So the real one should look like this. So let me use a different color here. Let me use black. So this is the wall here, and this is this wall I'm drawing. You have a bottom wall. Of course, this is a circular tube, and on the side of the tube, you have a diaphragm. So this is a diaphragm. Let me use a different color here. This is diaphragm. But instead of having such a shape, so you want to leave some thin film on both sides here. So that's why the real structure of the diaphragm should look like this. Sorry, let me use black. So this piece is a rigid block. So it is basically this piece. Let me use red one. And why we make it rigid is because we don't want a big deformation in this area. So most of the deformations are concentrated at those two locations. And because we want to use this block, let me erase it. We want to use this block to get in contact with the piezoelectric material. So that's why this is the piezoelectric material. And then finally, you have the final block. Let me use black. So this blocks you. So you can see once you have a, let me erase this. Once you have a pressure applied, so most of the concentration or most of the deformations will be concentrated at those two locations, and the middle part here is kind of rigid. So because you want it to have a flat in contact with the piezoelectric material. So that's the real design of a diaphragm for electrostatic piezoelectric sensor. So it should like that. So this is your stiff block, and then this is your diaphragm. So this is the flexible part of the diaphragm. So once we compress this piezoelectric material, it will generate electric charges on both surfaces, and the charge need to be amplified and finally converted into a voltage. So that's why for most of the piezoelectric sensors, we need one type of signal processing circuit, what we call charge amplifier circuit. So this is the circuit diagram. I don't require you to be able to analyze this, but you just need to know there is such a charge amplifier circuit. Just in case in the future you need to use this circuit for the real design, you can always refer back to the textbook. So let me briefly mention or briefly introduce this circuit. So this is a sensor part. If you can recall, this is actually the equivalent circuit of the piezoelectric material. So it is regarded as a charge source is in parallel connection with an internal capacitor. And then the rest of the circuit is basically the charge amplifier circuit. So you can see it has a capacitor, and it has another capacitor here in parallel connection with R1, and you have an operational amplifier. And finally, this will give you a voltage, and this voltage is actually linearly proportional to the charge build up from the material. So this is circuit, and I will not introduce the formulas between V1, V0 and the charge, but it's actually a linear relationship. So if you look at the textbook, there is a formula which can tell you the relationship. So those are the photos of commercial piezoelectric pressure sensors. You can see this is actually the diaphragm surface, and the inside is the piezoelectric material. On the other side is the electrical output here, so which refers to this part and correspond to this part.